Hello, anyone? Hello? Yes, we should be live right now. So, I'm ready to start working again on the RZT CPU. The last time I decided on some architectural choices which I made about the memory, particularly the instruction memory and the distributed memory. I decided to focus on a VRAM on the Xilinx FPGA. By the way, there are not good news about Xilinx, which apparently they're dropping their support for Linux, so not so fun. But anyway, I still have this beautiful board in here, which I hope. They were still keeping support for Vivado 2025.2, which I guess is the one I have. And then they're dropping it from 2026 onwards, which is a shame. I hope they reconsider this decision, but I cannot be sure about that. But yeah, in any case, we learned about differences about VRAMs and DRAMs, how they're structured. We learned that VRAMs are actually a bit faster than DRAMs. I'm wondering if this log should be a bit more detailed. Maybe it makes sense actually. I also decided to drop this section, or this section actually. I don't remember, but yeah, there are too many sections, and even now I'm actually thinking of adding another one. So today is 25th of May. It is a Monday, and actually let me just add a line here. No. Okay. And I'm not sure what are we going to do today, so actually I'm just going to write architectural choices part 2. So I'm going to keep the what do I want to do next, because I think it's useful. Okay. And then here maybe I can just write what did I do /learn. And maybe it does make sense. Yeah, we can keep it this way. So for now we want to continue looking at plan.md and make some more architectural decision. So actually let's reread this memory.md. We decided to go for a von Neumann architecture because I will just use one memory for both the instruction memory and the data memory. I'm going to use VRAMs. Instruction memory will be used in port A, which is read-only. Data memory will be used in port B, which has read-write accesses. Okay. I'm going to go, the theoretical maximum available memory is going to be 225 kilobytes, but I'm just going to use 32 because in case we want to have like decoders and encoders of video, something like that, we need other memory of some sort. So we can't use the whole memory. Probably I'm going to increase that to 64 kilobytes, but yeah, not now. So this means it is 8,192 words. The target algorithm is to minimize the area. Single byte writable. Native, so no XC interface. True dual port mode. No parity bits, no error correction because we're not in the space. I hope no background radiation flips any bit. Read first write mode. Enable pins. Register, no additional registers because we don't want to introduce extra latencies. And no reset pins because we don't want to accidentally reset the whole RAM. Pros, there are no structural hazards, maybe, because both the IMEM and DMEM will always have, no structural hazard regarding the memory, I guess, because both the IMEM and DMEM will always have separate hardware to access the memory, and there can be write collisions because the instruction memory is inherently read-only. We need to be careful to read-write collisions, and the memory is bigger compared to a single port memory because there are some extra flip-flops. Using read first grants that if the CPU reads and writes to the same address at the exact same time, the read port returns the value that was in the memory before the write started. Okay, so this is cool because we never lose the value, maybe? Not so sure, but yeah, probably. So, we decided about this. Let me actually see. Yes. I don't really like that. This markdown styling. Isn't there like a better markdown preview extension, something like that? Let's see actually. No. You see, this is one problem about Zip. There are not many extensions right now. But maybe with time it's gonna get better. Anyway, because it's really hard to read this markdown file. There is barely any difference between the normal text and bold text. But anyway, I think I can actually change that, but I don't want right now. So let's see. We answered these questions. We can remove all of this bloat. We can actually remove also the what the fuck. And so here. Okay. Let's see if it makes sense. Yeah, kinda. Fine. Then we can move on to the microarchitecture and execution strategy. Single cycle, multi-cycle or pipelined? I'm going to go for a pipelined probably. Execute one instruction per clock cycle, very low clock frequency, CPI equals 1. Easiest to build and work. Multi-cycle. I actually don't know. It may make sense to have a first simple CPU and then better refine it. But um, maybe we can make some decisions already, like some optimizations already here. I'm just gonna go for a pipeline, classic 5-stage, fetch, decode, execute, memory, write back. Oh, sorry, fuck, I deleted too much. Here I can just write, fuck. I'm going to go for a pipelined implementation, 5 stages. Pipeline implementation. I probably need to study a bit more the theory, because I know there are some much more advanced pipeline architectures, and we probably can do some research right now. So okay, at first I'm going to say code mentor, which is a skill I created to help me. I actually have a book in which there should be tons of information on this, but yeah, let's see. I'm going to save this and change the model to high. because I really want the answer to be as accurate as possible. It's very slow. Can I speed it up? No. I hate not having pin bindings in here. So let's put high. Let's see actually usage just to see. Okay, perfect. No, please. Okay. Nice. That's cool. Allow. Yes. In the meantime, I can actually see if. Yes. Oh my gosh. Why is it reading the same file over and over again? Yes. Okay, great. So let me see actually, because maybe I could have something inside here. Yeah, it should be this one. Should probably be this one. Yeah, wait, I'm gonna open it here shortly. So this computer architecture quantitative approach. I hope I can show this. I'm not sure. Memory hierarchy design, optimization of cache performance. This is really cool. This book is really a Bible. Instruction level parallelism. There is branch prediction. There are a lot of stuff. But I think we can all like do that later. Wow, this book is really awesome. pipeline. Yep, this could be a great resource. Great. So I'm probably going to copy this book over my repo because at this point it is useful. Where is it? Books. This one, gonna put it in where is it? Here in resources. Okay, I'm gonna give it a look to that later on. So let's see what Gemini actually answered. Let me actually see something in here. Superscalar. This is something actually interesting, which I think it could be really cool. But first of all, I'm not sure my FPGA can actually handle that. And secondly, it's probably something that we can introduce later. Wait. Of course, the website that Gemini provided are broken. But we can try to see that anyway. The Berkeley Automotive Machine. Wow, this is huge. This looks very interesting. Maybe before closing the live, I'm going to read this. Sonic Boom. No, fuck, trash that. Okay. And then the microarchitecture of superscala processors. This is from 1995. Okay. Okay, wait. So, I need to do something here. Okay, here I'm gonna write. I'm going to focus later on possible optimizations like superscalar or what was it called? Super pipeline. So yeah, this is decided. I'm going to go for a simple 5 stages risk. Wait, 5 stages risk pipeline architecture. Okay, then I guess okay, I can move on to the next question. For the target OS. I'm not really a problem right now. Not really a problem because we are very far from that. Not gonna concern myself with privileged mods right now. I'm going to implement only the unprivileged I say risk. I say and then gonna focus on the privilege mod later on. Buses and interconnects. A CPU isn't very useful without peripherals. UART, timers, external RAM. We design a custom simple memory interface or adopt an industry standard bus protocol like XC4 Lite or Wishbone from the start. I mean, this is not really problematic, but should concern myself right now. Just gonna say probably Axie, but this is a problem of my future me. Branch prediction, yes. If you choose a pipeline design, branch instructions will cause delays if you have to wait to evaluate the condition. I'm going to support branch eviction, but at a later stage, I guess. The later stage. So for now, I'm just going to introduce stalls. In the first version, I just need to be able to handle stalls and clear flush pipeline. Are you targeting specific FPGA? Yes, of course. I'm going to target for now the Basys tree with the RTX7. For verification, I have an idea as of now. Okay. I think that's all. So we have more or less a clear picture of what the CPU, what the first version of the CPU is going to be looking like. Check and see if I forgot to answer any important question before I start working on a V0.1 version of my CPU. Yes, the goal is to build. I'm gonna write that here actually. Yes. Yes. I can write that here actually. For the ISA, going to go for to start with RV32i. Yes. Okay. What? I can run a shell command from here? Why didn't you tell me before? Fuck. That's cool. Instruction fetch the register's value in the decode stage and put them back in the write back stage. Oh, fuck. Who said that this is synchronous? Oh no. So wait, I can't use... what are you talking about? Okay, yeah, the register file. And the register file is not the memory, so it's fine. Okay. Yeah, we also need to think about how to handle hazards. This is not important right now. Okay, so I guess for now this is a good starting point. I know which ISA I want to use, RV32i, which then I'm going to expand. The memory, we decided to go for von Neumann. Pipeline, of course, I'm probably gonna go with a superscalar later on, but for now I'm not just gonna be standard 5 stages with CPU. For the branch prediction, I'm gonna predict not taken right now, and that's it. Let me answer that. And then I think for today I'm going to stop here with the architecture. I'm gonna try to read this paper to see if we can steal some ideas. But let's see what Gemini answered. Okay. Sure. Okay. Actually, let me just try this. Ah, didn't know that. Okay. Cool. Anyway. So, let me update the log. Finalized the architectural plan. And then here I'm going to write reading sonic boom. I'm gonna create a new folder here, which I'm gonna call papers, where I'm putting the cool papers that I want to read. Documents, no. Encoding. RDC CPU. Resources papers. Okay. And I'm also going to save this here, maybe. Let me see. Yes. Going also to save this one here. But we are gonna start with this one. So let's see if we can learn something interesting about this sonic boom architecture. It's an out-of-order machine. Open source RTL implementation of RISC-V superscar out-of-order core. So it's a RISC-V superscar out-of-order core. It's the fastest open source core by IPC. I'm not sure what they mean here by IPC. Interprocessing communication, I'm not sure. Sonic Boom provides a state-of-the-art platform for research in high-performance core design by providing substantial microarchitectural improvements for Boom version 2. More significant performance gains are enabled by optimizations to Boom execution paths and a redesign of the instruction fetch unit. So, optimizations to Boom execution path and a redesign of instruction fetch unit with a new hardware. Okay. Stage branch. Okay, so they developed a branch prediction algorithm. Sonic Boom provides the first open implementation of a load store unit that can provide multiple loads per cycle. 2 times higher. This is instructions per clock. Okay. So this is the fastest open source core by instruction per clocks available. Available at the time of publication, which is don't know. But cool. Quite cool, to be honest. With this optimization, new features and can achieve 2 times higher IPC on spec CPU benchmarks compared to any prior open source out-of-order core. 6.2 core mark megahertz. Wow. Okay. Introduction. Microarchitectural timing attacks. What? Let's see. 12 and 14. Spectre attacks, okay. Yeah. Exploiting speculative execution. Probably gonna read that because this should be really interesting actually. And here, meltdown, yes, it's the other security vulnerability that affects CPUs. So, the recent disclosure of microarchitectural timing attacks on speculating cores injects a new concern into the design space. Architects must now consider security in addition to power, performance, and area. Yeah. As open source hardware implementation of superscala out-of-order core is an invaluable resource. Okay. Unlike a software model, a hardware implementation can demonstrate precise microarchitectural behaviors. Execute real application for trillions of cycles and empirically provide area measurements. Okay. Yes, they're saying that the open source cores are really simple, like this Rocket, Ariane, Black Parrot. I all want to read. I also want to read this. Want to see these cores. Rocket 3, 31. Okay, let's see 3, 31, and 21. 3. An industry competitive synthesizable parameterized RISC-V processor. 21. Black Parrot, an agile open source RISC-V multicore. Okay. And (31, 21, and 29. 31 and 29, I already did it, I think. 31 and 29. Wow, this looks very complicated. 29. Pico RV32 size of 2025 CPU. Okay. Gonna try to give it a look to that later. Maybe it would be cool to have some reading sessions where I read some papers. Anyway. Okay. There are also other ones. So, okay, they generated this sonic boom, which is made to be faster than the state of the art of that time, which I guess is like 3 years ago, 2 or 3 years ago. Table 1. Comparison of open source out-of-order cores. So the ISA, they're using this 564 GC. Others are using the same or 32. Million instruction per second. I don't know what is used for. It's 3.93. On the spec they are at 0.86. Pence prediction age. Decimal width. I don't know what that means. VHDL Kissel 3. What is Kissel 3, by the way? Gonna give you a look to this later. Anyway, Sonic Boot demonstrates improved performance and extended functionality compared to prior open source out-of-order cores. Furthermore, the configuration of Sonic Boom depicted in Figure 1 is the fastest publicly available open source core, measured by IPC at the time of publication. For wide fetch. So let's actually give a look at the implementation. No, actually, I mean, let's see step by step. We describe prior iterations of the Boom core and how the development history motivated new versions of Boom. Figure 2. Boom version 1 was originally developed as an educational tool for UC Berkeley undergraduate and graduate computer architecture courses. Boom V1 closely followed the design of MIPS R10K and featured a short, simple pipeline with a unified register file and issue queue. Boom V1 was written in the Kissel hardware description language and heavily borrowed existing components of the Rocket in-order core in its design. So basically, this Rocket could be maybe a good reference paper because it's simple apparently. So read papers. While Boom V1 could achieve commercially competitive performance in simulations, its design had unrealistically few pipeline stages and was not physically realizable. front-end execution units, MMU, L1 caches, and Python branch. Okay, we can remove this. I don't know why there are two fetch stages here. Queues. Okay, I got it. The code. Queues. Okay, so it's superscalar. Issue. I don't know what that is. Execution. Wetback. What is this issue and RRD? Boom version 2. Boom version 2 improved the design of Boom V1 to be more suitable for fabrication and physical design flow. In order to be physically realizable, Boom V2 added several pipeline stages to the front-end and execution paths, resolving critical paths in Boom V1. In addition, the floating point register file and execution units were partitioned into an independent pipeline. So it added several pipeline stages and execution paths. I see the same number of execution paths though. A floating point. Where are they? Builds upon performance in physical design lesson from Boom. The support board is a set of software stacks and address the main performance bottlenecks of the core while maintaining physical realizability. We identify key performance bottlenecks within the instruction fetch unit. Okay. Instruction fetch. Boom V2's instruction fetch was limited by the lack of support for compressed 2-byte RISC-V instructions, as well as restrictively tight coupling between the fetch unit and the branch predictor. Sonic Boom addresses both of these issues. Okay. Compressed instructions. The C extension provides additional support for compressed 2 bytes forms a common 4-byte instructions. Since this extension substantially reduces code size, it has become the default RISC-V ISA subset for packaged Linux distributions, like Fedora and Debian. These distributions additionally include thousands of precompiled software packages, providing a rich library of applications. Okay. To support the growing community-driven ecosystem of prepackaged RISC-V software, Sonic Boom includes a new superscalar fetch unit which supports the C extension. Okay. Sonic Boom new fetch unit decodes a possible 2-byte or 4-byte instruction for every 2-byte parcel. As an additional pipeline stage after the front-end decoders shift the decoded instruction into the dense fetch packet to pass. It's very complicated. And I'm quite sleepy, to be honest. Branch prediction. Where is the reference for the rocket? Rocket 3. Okay. So, no, it's not this. Okay. I can't find found. Okay. I'm not sure I can show this actually. Cool. Let me ask actually. Gemini, which I closed, fortunately. But there are some foundation, because this is very interesting but also very advanced. So some foundational papers on architecture that are more I mean, what if I search for Boom version 1? Yeah. This is lights. Hmm. Let's say foundational research papers that focus on basic or risk architecture. No, this is definitely not it. Let's actually open Scholar. No, let's use Scholar Labs. Okay, these are definitely too old. Don't care about this. No, I mean papers about physical risk because okay, for example this one. Linux capable rocket, the rocket ship generator, this one can boot Linux. Okay. Okay, this could also be interesting. Of course, the GitHub doesn't work. Let's call it Argent OpenSource 64-bit X5 application class processor. This is still opening. Okay, this looks cool. What is happening in here? Oh, finally. Okay, okay. So, for the next time, what I'm gonna do is read this and don't care about this. Let me see this shortly. Okay, no. And read this. So, read the rocket score paper. Read this. And then I want to read some chapters from this book here, computer arts quantitative approach. Yes. And I think for today it's everything. Yes. Okay. So let's commit. Okay, I don't care about this. Cache file. I mean, you can just yeah, trash file. Trash. What? Okay. So let's stage everything. Let's see what the commit comes out. Yeah, so in general, oh wait, okay, now high performance cores is definitely too much right now, so I'm going to go read the rocket core. Also next time I need to check what this keystroke is. Yes. Push. Okay. Nice. Okay. That's it for today. And I'm gonna see you next time. Bye bye.